phi, pi plus, pi minus. So this is a three-body final states, and there are possible intermediate resonances. So for the amplitude analysis, is to try to fit the data with all possible intermediate state to find what's the resonance in between in these processes. If you look at the pi-pi invariant mass, experiment one, there is a peak around F0 980, and then there are some other peak, maybe F2 1270, and some various peaks. So you try to construct the amplitudes. For some resonance, you may not know what's the quantum number. Then you should put all possible quantum number to fit the data and let the data tell you what's the quantum number. And for this, the first possible amplitude would be, since we know the JP psi is 1 minus the JPC is 1 minus minus, and then it decay to this phi is also 1 minus minus, and then the simplest is F0 resonance. They decay to pi plus, pi minus. So to construct the amplitude for this is one possibility. So you should first write down these amplitudes. So for the three-body final states, you can always separate first to two-body, then another decay to two-body. So by this way, the basic amplitude still is just a one-body decay coupled to two. And I'm not sure whether yesterday you already understand these principles for this one-body decay to two-body. Is anybody volunteer to write for this one? This 1 minus to 1 minus to F0, the covariant tensor formalism amplitude. Anybody know how to write it? This is quite simple. Simpler than yesterday's example. No? F0, this is a 0 plus plus. First, to this part, you don't need this part yet. So just 1 minus minus to 1 minus minus to 0 plus plus. What's possible covariant tensor amplitudes? Can any of you write for this in the covariant tensor formalism? Yesterday, I already showed you some examples. For this, anybody volunteer to write it? No?
So, directly this time is okay, so n must be even.
Sorry?
The granular part must be even, not 0, 2.
Yeah, okay. You want to write it? Yeah, maybe still you try this time whether you can write it correctly.
So I say L equals 0, and I have psi mu, phi mu, mu. So maybe I can do this.
Mm-hmm.
I'm not sure.
Mm-hmm. Yeah, that's a correct amplitude. Yeah, it's a. Yeah, anybody want to give different one? Yeah, this construct from G mu view and then two vectors. This you can you can write this way. It's same, just yeah. So it's
Write also maybe two.
yes, yeah, you're right. Yeah,
So I need now say if I knew
yeah,
T this was T2, so I could probably like this.
yeah. Yeah, perfect. So that's two possible. So, very correct. Yeah. So that only two possible amplitudes. One is with L equal to 0. Then just contract this two polarization vector. This is so it's good. So at least it's making progress and know how to write it. So for this, the first possibility is this. So the A1, then is what right here, psi mu, phi mu, and the A2 is equal to what he wrote here. For 2, it's just this. So we, in the general framework, I said first you get the A1, A2, then get C1, A1 plus C2, A2. This is including coupling constants to let the experiment determine this strength of this amplitude. But this is the only two. So this. Yeah.
You write a term with the epsilon tensor, with the g psi momentum and the relative momentum between the phi and absolute.
Okay, you said
Like epsilon mu
epsilon mu lambda sigma.
and psi mu phi mu.
Psi mu phi mu.
Right, and then the g psi momentum lambda.
G, J psi. Okay, and with the lambda.
Right, and then the relative momentum between the phi and absolute.
Relative between momentum between Q between phi and F0. Okay, this is so-called Q sigma. This is a covariant, but the problem is that this is a zero component here, and then you have this Q here, so that's a P wave. For the P wave, this is a parity violating, so this is forbidden. It's a parity violation, violating amplitude. Q, you have this Q here. Q corresponding to a P wave. You appears only once for this Q, is a P wave. If you write, in fact, you can prove that this is same. What you wrote here is the same as T1 sigma. So you are introduce only P wave, but as discussed, only L equal to 0 and L equal to 2. So that's only two possible amplitudes. Okay, so so this is for the first vertex, and then for this vertex, it's just a constant. I showed yesterday, it's just a constant. So for this, if you write the three body final states, then here you just add a Breit-Wigner for F0. Here you should also add Breit-Wigner for F0. Yes, so the amplitude for this process to F0 phi pi pi, there is two possible amplitudes. Whether it's 0 dominate or L equal to 2 dominate to fit the data to the data will tell you. And then besides F0, is possible to phi F2 then how about this one? It's more complicated. So how many possible amplitudes? It's also should use this LS scheme. LS scheme, what's possible? This is 2 plus plus. So spin 2 and spin 1 can form the spin 1, 2, 3. Yeah. So the total spin of this final state spin is phi 2 plus this phi can be 1, 2, 3. And also this L can be 0, 2, and 4 to conserve parity conservation. So L can be this. Then for the SF2 phi equal to 1, L can only have 2 to form the 1. The L. This must have L equal to 2. Do you understand? Follow this argument. Since if L equal to 0, the spin is, oh, so sorry. It's if spin is 0, okay, the L can be 0 and 2 to form the 1. So you have two possibilities. Then if total spin is 2, then the L cannot be 0 because 0 plus 2 equal to 2 cannot get this total angular momentum. And then this can only have L equal to 2. And then if spin equal to 3, this can be 2 or 4. So there are totally 5 possibilities. So you should construct 5 independent amplitudes corresponding to this 5 cases. So there are you should have I should get A3. Spin 1. A3 corresponding to this. This, I think, I may not ask you, I just write down directly. So it's you just think by yourself how you should write this. For this one, is straightforward. For the F, we always use a psi in order for psi mu is there, and then the phi view, F mu view. For this, that's the only possible way for this spin to couple to one and then couple to another one. So only scalar is this, and then you get this no orbital angular momentum part. Then you plus BW F2. And okay, maybe I not read here. And there is a propagator at here, PW F2, and also projector for spin projector of spin 2, then to contract with this. What you will get is just oh, sorry. Okay, this is F mu view. I should write more, not directly the final one. If you write, then you have this propagator, BW F2, then F mu prime, view prime, then times T mu prime, view prime. You contract this propagator, is just you get that. For this is this is this vertex. The first vertex is this, and then you have this propagator, and then you have this tensor contract with orbital angular momentum of 2. That's the T mu view is the orbital tensor for the pi plus pi minus relative wave function of pi plus pi minus. Pi plus pi minus should be in L equal to 2 state. So they have this wave function here, final state for pi plus pi minus. The orbital angular momentum, orbital part. So it's sorry. F2 is the intermediate resonance. After you summation over the, here have the M2, and you should sum over all poles for M2, that will get this, this spin 2 projector, and then you get this. So this is the wave function of initial state, psi. This is a spin function of phi in the final state. And no other spins, since the final state is pi plus pi minus. But pi plus pi minus is in L equal to 2 state. So you have this T mu view 2. So this is, you get this A3 for this. Then the second one, should be spin 1 coupled with 2, L equal to 2. That let me this spin 1 this spin 1 couples to 2. Okay, so it's put psi mu here. So this phi should couple with to form phi mu f mu lambda. Then this couple to 1 should couple to this L equal to 2. So T2. Yeah, so the first vertex is like this. This 2 couples to a vector, and then couples with this. You get like this. That's the for this first vertex, and then for second vertex, it's just the same as there. Then for this you can get, since this is replaced by T. Sorry?
Is there a difference between the capital T and the lowercase t?
Difference between which one?
The lowercase t, the third t mu lambda there.
T mu, this one?
T mu lambda,
T mu lambda.
that's the lowercase t.
Lower. This difference is this mu lambda is just you can have this you can let me see, you can write as T mu lambda prime, then with a G. Oh, sorry. You can just one is upper and the lower, but by change of the G. G mu.
One of them's an uppercase,
Yeah.
and one of them's a lowercase. So they mean the same thing. That means something.
It's a difference is just like ordinary, like a P mu or P mu. The difference is P mu equal to G mu view P view. So just by
Yeah, that's not. There are two different T's. One is small, one is big.
sorry, which you
Two different symbols. The small T, the big one, the lowercase and uppercase.
lowercase or uppercase. You can, if you, I don't, maybe you can write like this. The mu, you can, just the contraction of the index, you should also contract them. Capital T and the small t. Okay, sorry. The small t is orbital angular momentum between phi and f0. So you use the q, the momentum difference of phi and f2. And for capital T is the orbital angular momentum of the pi system. So it's the q you use is the 2 pi momentum difference. Yeah, so this is A4. Then for the 2 is also should be easy. Of course, you should have this other part. Then BW F2. This and the 2 should be also if formed 2 spin 2 is more complicated. Okay. This one should be quite relatively complicated because you want to form spin 2 from 2 and 1. That's if this subindex is 2, 1 to 2 is the odd number, you should introduce this upsilon, this kind of to get this. This oh, that's this one is yeah. If you can write this one, I think all the other one you should be able to. So this use L equal to 2. Then you have this T2 and T2, and then also the F2. This F alpha, let's write alpha beta, and then you should also have this and this. You should construct a scalar. So first, let's consider this 2, 1 coupled to 2. Then you can only use, note this, you couple this is just upsilon. Let me say coupled to 2. Mu should couple to 2, then should be phi view should be there. Then the F should have the lambda alpha. Then lambda alpha. This spin 2. Then okay. Then you should have this Jip psi for this sigma. Let me check. Mu star alpha. Okay. I write. It's better to put here alpha. You can see this P is from Jip psi. It's just for spin coupling. You should always use the parent momentum to be here, to contract it with here. This is the precise one. And this epsilon lambda after contraction of this, what left is alpha. And then you have another mu. So this is represent the total spin is a 2 for this for the first vertex. Then you have this to couple to psi mu. Yeah, this is most. This is what you write is a spin. This F2 plus phi spin is equal to this. This is how to couple this two spin to get this. This is total spin 2. And then you need to couple 2 with this L equal to 2. L equal to 2, then to form this 1. Then you this is a little bit complicated, but it's a psi mu should be here, and then you have this again. This let me. I shouldn't use here. I should use. Alpha, you use beta is better. Use beta, not T. To keep always use the mu for this. Then you have this mu. Try to spin 1, 2, spin 1. Okay. Is, oh, sorry, is this a mu prime. What I can use? Alpha prime, beta prime. First this, then with this p psi mu prime, and then this s. Oh, is alpha, beta, and then this T2. T2 should have the alpha already, the beta prime, and then the beta here. So that's all the. So you can get like this. This is one beta is contracted with this, and alpha is, since it's a spin 2, then spin 2 to couple to spin 1, you need another this antisymmetric tensor. And by this, so the final amplitude should be use this one, and then with the propagator of this, then I can. So the usually for initial states, there is this bracket. You should have this complete conjugate. Put a star there. I haven't put this, but one should put for the initial state. Put a star here. But, something like this. That's this one is the most complicated one. Since you need to construct this from the spin 2 coupled to spin 1 to form spin 2. That's no easy way to contract to be scalar. Then you must introduce this anti-symmetrical one to get this. And for second coupling also need this. Yeah, okay. In principle, you can. Yeah. You set up, since now there is a FDC using the Feynman diagram, Feynman diagram, automatic calculation or something. You set the rule, then it can do, but first you should set up the rule like this, and then if the computer program is good enough, they may. And in fact, for the baryons and for the mesons, we have people develop for this. When we have the group at IHAP, for baryon we already have, and for the mesons we also have for some, at least for some simpler cases. If you put into the rule, then okay. But you should first know the rule, how to construct them. So for the third, for the three, this total spin 3 is quite easy. Since you already have F alpha beta, then with phi, you just have a gamma. This is already spin 3. That's quite easy. Then you have this coupled to the T2 coupled to first to the T2. Then you just have beta, gamma, and then psi, alpha. That's straightforward. It's quite easy. If sorry. The psi star, yeah. Okay. If I change this mu, I should, if I use this, sometimes I should keep the first psi mu to be same, but you can easily adjust. Just need to contract them. And then mu view, and then phi view. Sorry, T mu. If I use this mu prime, this mu view. I forgot. Yeah, this mu. And then if you continue for this T mu view, I will just L equal to this you can change it to this T2 mu prime BW F2. So it's how many I have written here? 4, 5, 6, 7. Okay. The final one is also quite simple. Since you have this T4, L equal to 4, and that's spin 3. That's quite straightforward. 5 view, and then is this is quite simple. So we have three. For this we have 5 independent, corresponding to different LS. So this is all possible amplitude for the F0 for F2. For F0 there are 2. So if only this resonances quantum number there, then you already got all the formula. Then have the parameter to fit the strength of this to determine which amplitude fits the data best. And all the data will tell you which one is needed. Give you the strength. So I run the all possible amplitudes. Then you can and then from this we can get this probability function. Since yesterday, we said yesterday we said should be read something like a CI AI, and then yeah, the AI is equal to this contradict with this. I just use this things. Then the d sigma d phi 3 should to take average of the initial state and take the sum over the final states. So it's a oh, here should also the initial state for the GPSI is produced from E plus E minus. I mentioned yesterday that from E plus E minus due to gamma mu coupling is a helicity conservation operator. They will get only polarized GPSI. It's along the along the beam direction +1 and -1. There is no 0. And for the phi, it can be 3 possible projection. And to get this formula, I used this I think on the first day we mentioned that this is used this one, the sum of the M2, this times this 2, you can get that one, okay?
In general, the CIs and the CJs, I always thought they were like couplings. So, can we assume that they're real?
It's in principle, it's complex.
Okay.
Yeah, it's a complex number.
Okay.
Yeah.
How do you relate that into the couplings then?
Here is let me. Yeah, it's a strength. It's for this amplitude. It can be complex, constant. Yeah, the different amplitudes may have the relative phase. Yeah.
Is the real part then the couplings?
Sorry?
Is the real part of this C like the couplings?
No. I think it's the total strength. Like a rho coupled to pi, we use a coupling constant, but in principle, relative to other processes, it can be a complex. Yeah, it can have a relative phase to other amplitudes. And I also used m equal to 1 to psi mu. This is just delta mu prime, and then delta mu 1 plus delta mu 2, and then you will get this this formula. So you get this, then you use this probability density to fit the data what the experiment measured. This for these final states. Use what I mentioned yesterday is family or minuit. Then you can get this various parameters to fit into the data. So what time we should have a break? Maybe we have a break now. Take 5 minutes. Yeah. So I think. So, okay, let's start the second part of this lecture. I just showed you one example. For other example, it can have this F4, spin 4, or any spin number. You can write this similarly with this LS scheme. How many different LS coupling you will get different independent amplitudes to get. And that's for the Meson case. Then we come, now I give you some example for with photon. Psi to gamma, K plus, K minus. This is very similar to, seems very similar to that one. This gamma also is 1 minus. So this so here for the F is also possible to be scalar F02, but because this gamma is different from phi, the difference is the gamma have 0 mass. So compared with the formula here, it's just the phi mu should go to E mu, the polarization vector for photon, and that's for the phi. For phi, you have 3 components, but for E mu, it's different. You only have 2 components for the real photon, only 2 possible projection, and we know that similar as phi is also should. If the full momentum is q and the full momentum we write k equal to 0, and also q square equal to 0. That's a major difference. And the simplest, usually we use a Coulomb gauge. Coulomb gauge means in this system A0 equal to 0, it is equivalent to P mu E mu. Equal to 0. So if you have this, then E mu, K mu, K is this momentum is also equal to 0 because K is equal to P minus Q. So you have all these properties. And also for for this sum over the final polarization projections, you get this G mu view. Then for the photon, the main difference is this summation. When you make the final state, is equal to G mu view plus Q mu K view plus Q mu K view plus K mu. So we defined this by this. So this replaces the previous G title for the vector meson with mass. Without mass, for the photon, one should use this one. Then you can do summation, use this one. Then all the gauge invariance problem or everything, you don't need to worry. So just replace that. Replace the formula there, G tidal mu v with this double perpendicular one. This you can, in fact, this formula is written in the textbook of Greiner and Schaefer. At Frankfurt on QCD. That's for photon. Sorry? Q dot K. Q dot K. No. Q dot K. The final state Q dot K. Q dot K. Now it's two real particle Q dot K. You see Q dot K equal to Q0 EK plus Q squared. At rest system, this is a Q. This momentum is opposite, so energy is positive. Q squared is positive, so it's always positive. Cannot be zero. Q dot K. Yeah. It's for the real photon here. Oh, sorry. Appeared twice, yeah. Sorry. Yeah, like this. And with this, you can write a formula similarly, but now the independent amplitude is reduced. For example, here, the first one is okay. Still, you just replace it by A1 equal to process star mu E mu, then propagator. But then for the second one, if you still use this one, is if you use similar thing here, you see here is if you write out, it's just something is between the T mu view is you can, we know the T mu v 2 is equal to, how to say, this is composed of the definition of, you have this Q minus K something. Something like this, and then with some number, then there is G mu v dot Q dot K, or something like this, and with this, the E mu contract with one of them. Since E mu is times this equal to 0, you will show that this, you will reach to the, you can prove. It gives the same angular momentum distribution. So it's not an independent one anymore with the photon. So for the photon, they will be, for F0, will reduce to only one independent amplitude. And for the spin 2, you can show that you will reduce 2, so only 3 independent amplitudes. That's the difference. Otherwise, you just use this formula to fit the data. But for the photon, the number of independent amplitude is reduced. It's come from this Q square equal to 0, and also the gauge variance limit, something constraint, more constraints, and you will reach this conclusion. There is only one independent for F0 and 3 independent for F2 for this. And then with this, you can fit the gamma KK data. That's for the photon case. And for, I haven't shown here, for the 3 different amplitudes, if you plot the cosine theta gamma distribution, they will give different amplitude. And then for the k-on, for different projection, so, for KK, in iterator system, some will have such shape, and some others may have. So different independent gives a different distribution, angular distribution, and the data, fitting data can tell you what's the dominant amplitudes. Yeah. Okay, that's what I want to know for the examples for the photons. For others, with more particles, it's similar. You just remember this for the photon, the difference. And the next one I want to introduce about the baryons, the fermions. All previous formalism is for the mesons and the photon with integer spins. And then we know that for the baryons, it's half spin, so they are different. So I will start from here. Since in ordinary quantum field theory, when you study is only spin half and spin 1, and maybe sometimes spin 0. But in Hadron spectroscopy, it can be spin 7.5 and spin 4, spin 5. So you need to use a different formalism. This basic, the basic difference is for the spin half, is most elementary one is a spin half wave function, and the projection operator, and the propagator. We start from spin 1, spin 1/2, then we go to higher spins. First wave function, I think most of you knows, but I still write here. Since it's a basic building block for higher spins. And this is a normalization. It's maybe different textbook use different convention. I used to use Itzuksen and Zuper. I'm not sure whether you use this textbook for quantum field theory. Itzuksen and Zuper. I use his convention, their convention. And this is just a well-known one. Then for the antiparticle, this wave function is a standard. And then for the projection, this is a wave function. Then for the project operator, I think you should also already know. Since Professor Roberts already showed many times this. And lambda minus. For this and this, I think you. the propagator is just sum of this, and the is like, oh, sorry. It's standard, like, so with this is for spin. It's for spin half. This for higher spin is very similar for the integer number. Just for example, for the 3/2. For 3/2, then the wave function is just so after you know the spin half, then just by CG coefficient to combine spin half with spin 1, then you get spin 3/2 with CG coefficient. So by this, you add just like for this mesons. For higher spin, you just additional ones into it, and then you get arbitrary spin wave function. For it's just this is if you use S as for SC, just the CG coefficient there is So it's for n plus 1/2, just use this spin n tensor, then construct with the spin half, you get the higher one. So you can get the wave function for arbitrary spin for this half integer. And there are various couplings but what I want to recommend is use this LS scheme, just like similar as this for the meson. It's quite easy to determine how many independent one. I think for you, let me maybe give some example. Like psi decay to let me think. For half, for the meson coupling, maybe if let me think what I should start. For the n star goes to n pi. Sorry? K bar? P bar? Oh, okay. This is antiproton. Yeah. Let me think. How should this? Usually, for the simplest is like half minus to n pi. This is quite commonly 2n pi or n eta. That's just a gamma phi coupling. And also, we know is use this U n star. And then this gamma phi coupling. And that's commonly used. This is this is half minus. This is half plus, and this is 0 minus. This is in S wave. There is only one possible coupling. Then you can. This is a well-known one. It's a simple, but for higher spins, there are. Like for vector meson, for vector meson, like for rho, is 1 minus. The most 1 minus plus. This most commonly used is gamma mu gamma phi. Maybe use the proton is better. You may be more familiar with this. Is a usual gamma mu. This is similar as for the photon coupling. Gamma mu is most well-known one, this vector coupled to this. And then people use another sigma mu view, q mu, this kind of type interaction. There are two independent ones. Why there are two independent? One is because they have the L equal to 0 and L equal to 2 can have. In principle, there are two independent ones. But when you write this, like this two independent one, you will find it's not pure S wave. For this gamma mu, it's not a pure S wave. And for this, it's not pure D wave. It's a mix of S wave and D wave. And but there are two independent one. You can use any two independent one, but the linear combination you can get pure S and pure D. What I in the paper I listed on the first day by myself and Hussein, we tried to use the LS scheme for higher spin. Otherwise, it's you need to construct for higher spin is not so systematically. If you with LS, then it's straightforward. You know how many independent one, how to construct. It's relatively easier to follow. And here I just introduce what we used for this LS scheme. For the LS scheme, for example, for this for decay A to B plus C, B is N star, and the C is P bar. This is a spin half, and this may be N plus half, most general one. So we try to introduce the pure spin for this, the sum of these two spin. The pure spin, not including the momentum dependence. Then we if SB equal to N plus 1, and for this, SB equal to N plus half, and SC equal to half. Then we introduce SBC equal to N. So first couple B and C with pure spin, and we have spin N plus half coupled with a spin half. It can be either N or N plus 1. Only two possibilities. So we combine these two spin first. Then after you get this, you get this sum this two half, you get an integer number. Then you can construct invariant as for mesons. Then just follow the previous for mesons. You can get everything. So we tried. So for the this we use this bigger number, capital. Oh, sorry. Oh, maybe can you see here? Or? Here, you cannot simply use gamma mu. If you simply use gamma mu, as I said, it's a mixture of this mixture. We will introduce some Q-square dependence. This R is defined as a momentum difference between these two, and should divided by the sum of this mass. And in the paper, we showed that this gives no momentum dependence, only the spin part. So this you use to construct the spin n plus 1. This you get a spin n. Then with this spin, this term is symmetrized. This mu1 and mu n plus 1. We know this should be symmetrized. Here is already symmetrized, but this you need to symmetrize this. We know for the A decay to B plus C, we should have the SA equal to O is a vector, is not a simple number. And you can just okay, for this is okay. Since we already get the SB plus SC with this, then combine with this tensor orbital angular momentum tensor, you can get SA. SA is also integer number, and now you equal to so with this definition, you can just get use what we used for the meson, for the integer quantum number, and it's straightforward. This is from meson case. Another case is if A is n star, decay to n plus some meson. Then we should, this you can also write is minus SA. So we should first combine the spin of these two to get this quantum number. And this is different from that. For SA, this will spin n plus half. This spin half. For this, then the phi coupled to n is we can also find, this also should be symmetrized. Then we also combined these two first to make them to be integer wave function. Then all others just follow the similar thing for the meson case. So for the baryon part is also, if you construct this, then you can get the independent amplitudes. You just study how many different areas couplings and how many independent ones. Then similar as for the meson case, you can construct the independent amplitudes. Then fit to the data, you can get which amplitude is dominate. Yeah. Also, okay. Yeah, I should stop here.